get used to it and adapt. So we fixed this part. So I explained that. I hope it's clear. Now let's get to this. And as I told you that it's a polynomial, so most likely you have seen this. So what I'm having now on the whiteboard, you have seen this way to write equations, and you see that it's familiar. You might not remember how to get x out of it, but you might see that it is familiar, right? Right. If it's not familiar, it's okay. Don't be scared again. So why did I write this? And what is the common points with the initial equation with an exponent? Well, if I'm saying right now that e to the power of x, let's call it t. Usually that's how we do it. So e to the power of x is equal to t. And then let's go back to the initial equation and rewrite it in terms of t. Okay, we now know that e to the power of x is equal to t. So e to the power of 2x is what? Is e to the power of x squared. So that would be t squared. Then I'm gonna write minus 2t, because that's how I replace e to the power of x. I said I'm gonna use t, and you're gonna see why very soon. Minus 8 equals to 0. Okay, so this, I just pretty much rewrote this thing with t. So let's delete that for it not to distract us. Great, so here how do we solve it? We just need to find t, right? So we need to find t. You can go about it with a discriminant. You've heard what discriminant is. And then another trick here is to use the theorem that I don't know how to pronounce in English. Viet, I think. What is the theorem? So let's check. Now I'm taking a very general case, so I'm gonna get back to my t equation. Dun, dun, dun. X squared minus plus bx plus c equals to 0. So what happened? I just rewrote again the same thing in general form. So using b and c as coefficients. And given your coefficient to x squared is 1, it's very simple to find the roots of this equation. So the theorem goes like that. X plus x1 plus x2. So we know that there will be two solutions to this equation because it's a square equation. X1 plus x2 is equal to minus b, and x1 times x2 equals c. So this is a theorem. Write it down in your notebooks if you forgot it or never seen it. That works for any polynomial. So, I mean, what did I just say? It's not a, well, it works for any squared equation. And now let's get back to our t, right? So let me write it here. Oh, wow, nice. In our case, t1 plus t2 is going to be equal to 2, okay? At the same time, t1 times t2 T1 times T2 is going to be equal to minus 8. So now what we have to do is find two numbers whose sum is 2 and the product is minus 8. So certainly they have different signs because the product is negative. The sum is 2, and how do we get 8 as a product? Well, it should be 2 and 4, and one of them is negative, and it's gonna be 2. So the answers to this equation, so the solutions of this equation, let's do something like, or not like that. No, that doesn't work. So this is our theorem in general. I'm gonna tell you tomorrow what's the name of the theorem. And here we have T1. Well, let's write it like that. T equals minus 2 or T equals 4. That's what we said. Okay, and now let's get back. We remember that T is e to the power of x. Sorry. T equals minus 2 or T equals 4. Oh, given you're super bored right now because you already solved it 100 times, you can go forward with the presentation, just solve logs and be very happy and proud of yourself. Alright, so let's get back to where we started from. E to the power of x is equal to t. So what we got is pretty much e to the power of x is equal to minus 2 or e to the power of x is equal to 4. And now what you should notice is that this is not feasible. Well, no, this cannot happen. Why cannot it happen? Because I showed you the exponent plot. It is all the time positive. Well, any exponent is positive. So this cannot be a part of a solution for x. So with this we do nothing. We use the second part. So we see that e to the power of x is equal to 4. Now we understand that x should be something that we should raise exponent to the power of this to get 4. So how do we write what's x? Well, that's where we start using logs. And for this exact problem, the answer will be x is equal to natural logarithm of 4. And if you remember the formulas of, the rules of dealing with logs, you can see that this is natural logarithm of 2 to the power of 2. And that can be rewritten as 2 natural logarithm 2. If you don't remember anything about logarithms, well, the last part of the class is for you. And I really want to finish it today. I think we're gonna have time for the questions. So here we go. Logarithms. So what's a logarithm in general? Well, a logarithm of a given number x is the exponent to which another number, let's say b, base, must be raised to produce that number x. So with the previous example of, in here, I think you already got the idea of this transformation that logs allow us to do. And ln, again, I didn't say it out loud, ln is natural logarithm, so logarithm that has e exponent for its base. So now if you still don't understand how do logarithms work, I think the best idea here is for you to look at these examples and really try to understand what happened here. So from this writing, we can pass to this. So given b to the power of a is equal to x, then the logarithm of base b of x is equal to a. So this dummy way to remember what's logarithm, you should always tell yourself in your head, logarithm is the power. Okay, so here it was a, okay, the logarithm is a. Here it was a, the logarithm is a. I don't know why I put parentheses here, but just not to confuse and not to read it like Linux. Okay, so great. Take your time after our class to get used to this, and I'm gonna send to everybody who asked me the extra exercises. And even the better idea is that I'm gonna send extra exercises to everybody. So you're gonna have a homework for tomorrow, and then I'm gonna LaTeX that, because I don't know very much how to do these things. So sometime tonight, or for some of you today, or for some of you tomorrow, I'm gonna send those extra exercises. And if you understood everything, just spend your time, doing something better. If you feel like you need to practice more, that will be your fun for the next 2 weeks. Okay, so back to logarithms. What we have here is the identities, so the rules of using logarithms. They actually are derived in a not very sophisticated manner from the rules of exponents. So, for example, this one and this one result into these identities. And then very, very, very important thing that you're gonna remember, and if you don't understand logarithms and don't want to understand it, well, just please memorize this stuff. This is gonna be used in economic growth a lot, because as you've seen already, the utility function that I've shown you, it's always the discounting of E, and you can have this power. And if you know how to simplify it, you're gonna be way better off than if you don't. Okay, so these identities, you have them, you have the slides, all cool. Logarithm plot, so that's how it looks like. And we're gonna see tomorrow with the functions topic that they have a lot in common, logarithm and exponent. I mean, the graphs. So this one and this one, they're somehow connected. So passing to the application in economics, logarithms is really something that you're gonna see everywhere. So first of all, just a function of logarithm is one of the most common utility functions. In micro, in macro, not so much in growth. In growth, you'll have more of exponents. That's the first, I didn't even write it here. Then, what is great about logarithms is that they transform nonlinear functions into linear functions. Not like they transform it, but we can always write a linear approximation of whatever function we have. And this is great for econometrics. Yeah, it's great mainly for econometrics, and you'll see this linearization in front of your eyes. And sometimes, well, given you take next year something like business cycles, you're gonna see the linearization of ugliest things. So from something that we don't know how to work with, we come to something that we can operate with. So logs are used to linearize whatever we have. Logs can be used to model a percentage change. This is going to be in a regression, the first presentation of econometrics, you're going to see that. Then elasticity, you're going to see that again. And the logistic regressions, like somewhere in the middle of econometrics course, you're going to have it as one of the ways to model probability. So, this is just to stress how important logs are, and not to scare you, but to motivate you, to work on logs a little more. Great, so we have time. So let's get to exercises. I'm gonna leave my slide like that. You have the presentation, you can scroll through, you can go back to these things, you can spend some time understanding what's logarithm. And that's gonna be our final stuff for today. And I'm gonna try to go step by step, except for the last one. The last one is something that you're not gonna need. And really, if you don't understand, well, don't bother, because you have to, catch up with more important actual practical stuff that you're gonna use. But if you wanna, provide me a nice proof, that's good. So you can do that. You can have fun with the last part. And just, to show you, because, well, if you know how to solve them all, go ahead, solve them. But before that, I wanted to show you some examples. Also asking you, how does it work? So we are all on the same page. So first of all, a natural logarithm of e to the power of 3. Okay, so great. So how did that happen that we got 3? Just by the definition actually of logarithm. So we know that logarithm is a power to which we're supposed to put, in this case, since it is a natural logarithm, it's a power to which we're supposed to put e exponent to get the number. And our number to get, so x here, it's e to the power of 3. So obviously the power to which we're supposed to raise exponent to get exponent to the power of 3 is 3. So this is major identity, okay? Again, you can just memorize it and then understand with the other examples, just use the same logic. So this, write it down, read the letters and put it above your bed. Okay, so cool. Now let's do something that is not natural. Logarithm of base 2 for 4 equals 2. Again, use the chat to let me know the answer. 2. Cool, yes. So we're supposed to raise 2 to some power to get 4. And this power is 2. You're not gonna see logs with a base. So what you're gonna see is always natural logs all the time, because that's something that is conventionally used to linearize, to calculate percentage. We could choose whichever base, but we decided to choose e. So because of many reasons that you can read about or forget. Great, so now another one before we get to exercises that you already have. Natural logarithm of square root of e 1 over 2. It is exactly the same as the first one, just to remind you that square root is exactly the same as power 1 over 2. Okay, let's write it somewhere here because I don't want to scroll anymore. Oh, it's a big one. Okay. Dun, dun, dun. 6 plus log 3, 9 is equal to, it's going to be an ugly thing, it's not going to be a number. Write it in the chat. No, don't use calculators if you already started, because I don't know the actual exact answer in numbers. It's easier than you think. It's just using the formula. Okay. It's even easier than that. What I wanted you to use is this thingy. Well, 54 is already something on the line. 3 plus log is okay. Maybe some of these numbers are okay because I didn't do the calculator. Okay, yeah, that's the one, that's the one. So, I didn't want you to do any modifications and find a number. I just wanted you to use this formula, this identity, this rule that I highlighted in the slides. So, you end up with log the same base 3, right? Of what? Well, you multiply six and 9 and get this. That's it. It's like using the identity but inverse. Yes, the last one, if you go this way, extra. But well, what I wanted is just this. Okay, cool. And the last one before you solve the exercises is going to be this one, log 2e. So, well, you can just be like, it is what it is. But I want you to do the transformation and express this stuff in terms of natural logarithm. So, try to do that. I left the formulas on purpose on the screen. So, just write whatever you think is correct in this case. You're using, actually the highlighted formula. Yay. Yes, you're right. So what's happening here? We're just changing the base. So this formula is called sometimes passing to a new base formula. So here we had the base of natural logarithm is e, and x as the number, and we can rewrite it as a fraction. What for? Well, sometimes we need natural logarithm because we know how to In econometrics, we have something already expressed in natural logarithms, and we need everything else to be expressed the same way. So this is what we use. We end up with 1 over ln 2. Okay, great. So this is the general logic, and it's great that I showed you these examples. So now you go on, solve the things. Again, for everybody, just the first 2 blocks, calculate and solve the following equations, and the last one is just for you to have fun. I'm not gonna even talk about it. But given you don't have anything to do, you can do that. I give you 5 minutes, so at 29 we go back. Okay, let's get back to it. And the first 3, well, someone already told us the answers, and they're actually correct. So look now. Okay. For the first 3 calculation exercises, the first one, I'm gonna say it like orally now, because I want to show you more of equations. And if you didn't get it for now, like how to actually calculate this log stuff, it's okay. You should take your time on your own. And then obviously I'm gonna send more exercises, as I already mentioned, and you can always, contact me. For this week, we might schedule 1 office hours. I live very far from MSc, so I don't go there very often, to be honest. But if we have a lot of people, so don't hesitate to send me emails saying, I don't understand anything, I need office hours. So I'm gonna explain it now, why it's not 3. So again, the more emails I receive, the more likely it is that we organize something this week. So to just close this week and start next week fresh. And why the first is not 3? So what is written here? Oh, because 3 to the power of what equals 1, which is 0. Because 3 to the power of what equals 1. Okay, yeah, exactly. So as we remembered already, logarithm is the power. So in this case, what is written is the power to which we're supposed to raise 3 to get 1. And how do we get 1 raising 3 to a power? Well, the power has to be 0. Okay, so any number to the power of 0 is equal to 1. I didn't say it yet out loud, but yeah, let's write it down here. Wait a second. X to the power of 0 is equal to 1. So, consequently, 3 to the power of what is equal to 1? 0. I agree absolutely with Anthony's explanation. The next one, that we got 81. Well, how did we get 81? Because what is written here is that 3 is raised to the power to which 3 is supposed to be raised to get 81. And if we raise 3 to this power, what do we get? Well, we get 81. Again, this thing, do I have it here? It's like this. So here what we have is e raised to the power of natural logarithm of x. So to which power we're supposed to raise e? No. Okay, the last time I said it better. I don't want to confuse you right now. But anyways, so this is the same idea as this. Except for this is not natural logarithm, this is the logarithm of base 3. Okay, Next one, you were supposed to use the formula. You were supposed to get 75 divided by 3, supposed to get 25, and the logarithm, oh, I can write this, so you also remember something like that. Logarithm base 5 of 25, so to which power we're supposed to raise 5 to get 25? Well, to the power of 2. Okay, great. Thank you. And now let's get to the equations. Just a real quick question. Whoever got the results for the first equation, because second equation is really but for the first equation, write it please here. So I confirm my, yeah, okay, good, I confirmed. Great, thank you. All right, so how did we get minus 1 over 4 out of this ugly thing? So we have logarithm to the base of 4, 0.5 plus x. See, now I'm improving, I'm typing faster, so by the end of this week, most likely I'm gonna be super fast. Okay, so again, as in the case of the powers, it was long ago, like here. If we have, here we had base, let's say 4, and exponents x and 7, we understand the same base means that x is equal to 7. Here, what we can have, like, I'm gonna write it just here, you know, like, ding, ding, ding. Given I had something like log 4x equals to log 4, 7, I would know that x is equal to 7. So again, all I have to do is to express this minus 1 in terms of a logarithm that has a base of 4. So log 4 0.5 plus x. Okay, shouldn't have said that, I'm getting better. All right, so look what is happening. We're saying that the power to which we should, I don't know why I wrote it again. I'm not supposed to write it again. The power to which we raise 4 to get this thingy is minus 1. So that's what is written. Again, logarithm is the power, it's the exponent. So we raise 4 to the power of minus 1 and we get this. 4 to the power of minus 1 to the power of minus 1, perfect, is 0.5 plus x. Okay, great. Now, 4 to the power of minus 1 is 1 over 4, or I can write it 0.25. 0.25 is equal to 0.5 plus x. X is equal to minus 0.25. Minus 1 over 4, as you all correctly mentioned. So now the last thing to solve is this beauty. This is a logistic regression. So we want to find a probability. So the way, what can we model like that? Like, for example, a probability, my favorite example, a probability of, how do I say it correctly? Establishing a successful academic career if you are a woman, have kids, if you are of ethnic minority, well, anything you can imagine goes as regressors here. So like this will be being a woman, this will be being married, blah, blah, blah. And then you model a probability. With different data, you find this probability. So the way logistic regression works, it works like that. So by asking find P, what I'm really asking is find that actual probability we're talking about. And it's gonna be a really nasty long expression that I'm gonna write down for you. Like when now we finish our class, I'm gonna write it down. Just the beginning of how you should start handling this stuff. Well, like that. P1 minus P equals e to the power of, now I'm gonna have this trouble. E to the power of y, where y equals our thing, beta 0 plus beta 1 and plus beta 2. Okay, so this is the equation that you start with. And what I did, I just translated what logarithm means. So it's a natural logarithm. So this is supposed to be a power to which I raise e to get this stuff. Alright, so obviously you understand that there is a white noise missing in this regression if you are very familiar with econometrics. And if you're not familiar with econometrics at all, well, here absolutely no need to worry because that will be explained to you very well in detail during the econometrics classes. So